Okay. So is screen shared with you?
Yes.
Okay. Ji. So today we are going to discuss the topic where we left over. We were talking about Young's modulus extension and all that stuff. Got it? So I'm going to extend this topic to the next level. That is to determine the Young's modulus. To determine the Young's modulus. So when we are going to determine the Young's modulus of any wire or something which is under discussion, for that one, what do we do? We just make such an arrangement that we can find its Young's modulus. Uh, Graphically, we can find it out, but I will let you know the graphical method later on. First of all, there must be a wire, okay, or any stuff which is to be stretched or which is to be tested, and then along with that we must have a load. We must connect a load with that, a mass hanger type thing, okay, and that mass hanger will be just mass hanger will be that will be used to keep the wire straight, right? It would be clamped here. Yeah, I mean, you can hold it either in the lab with the help of your clamp and boss or whatever, but you can hold it. So this is a load at which this is your zero load. Zero load does not mean that it is zero. It is just to keep the wire straight. To keep the wire straight. Okay, got it? So
Yes.
here now, when the wire is straight, you will check that is there any along with this wire we will have a ruler or some sort of scale that is called the Vernier scale that would be attached to that. Okay, there are two methods. One is the Vernier scale method. We will use a instrument which would have uh, some sort of mechanism inside, that when the reading would be changed, the yani when the wire would be extended, the wire would cause the reading to be changed. Okay, nine. This is the owner scale. So what do we mark actually, or what do we notice down? This is the zero position of the wire. Here we just place a marker. Okay, we place a marker here, and we add the loads here. We add the loads, and when we will add the loads, definitely what will happen, this marker would be slided down. Okay, and when this marker will be slided down, you can say that this is basically attached with another rope or another string, this this Vernier scale or meter rod, but it can be anything, but its accuracy would be more. So when the pointer is now at this position, from this point to this point, this is your extension, right? So this is what what do we do? But I will not write all the procedure here. What will I do? That the variables you are using loads of various masses. Okay, first of all, this is your interest, and then you measure the initial length. I will write here. uh, just a second, I would write all here. Okay, what will you do? You will measure the initial length of the wire. Okay, measure the initial length of the wire. Initial length L naught of wire. Then measure diameter of the wire from different sections. Okay, Mayer, diameter of the wire from different sections
Okay.
of wire from different sections and take average. And take average, right? Will you be able to do that?
Yes.
Okay. Then after that, that will be your D average, or you will say that is D, that is your L naught. Then measure the, sorry, add the loads, add loads, and, or you can say add loads and note down the new length of the wire. Okay, it is L. Then after that, what will you do? You will find extension for every load. Find extension for every load. So when you are going to find extension for every load, that would be noted down. And finally, you will plot all the values and make a graph. Plot all the values or all the readings and make a graph or draw a graph, right? Then I will let you know that how to handle that graph. But the graph will be graph of graph of load and extension. The graph will be between load and extension. Got it?
Yes.
So when I will move to that point, I will say that in this case, your graph is something like this. Because for the load extension graph, it starts from 0, 0. It is your extension, or sorry, yeah, it is your extension in centimeter or millimeter or whatever, and this is your load in newtons. So if I have a graph of that, then what will be its gradient? Yes,
Uh,
its gradient is extension divided by load, which is basically your spring constant. We have studied about that. But it is how will we relate this with extension? Sorry, with Young's modulus. As you know, that Young's modulus is equals to 4 FL divided by pi d square E. Right? Pi d square E. Are you agreed?
yes.
So if you agreed, then just make this all outside pi d square, and this is your force divided by extension. Got it?
Yes.
It means now your Young's modulus is 4L divided by pi d square into gradient of the graph. Is this clear? This was what I'm talking about. Clear है? So first you have to take gradient, and by taking the gradient you will be able to find the Young's modulus of this wire. Okay, you done?
Yes.
Okay. So right after that, we will go to the other graphs, the graphs of stress and strain graphs. Right? Before that, we have studied about Young's modulus, I mean, the extension and load graph. So if we go to the Young's stress and strain graphs, you know what happens? That when there is a stress and strain graph, if this quantity is stress, this is your strain, then within elastic limit, the graph would be straight. But after that, there would be a necking effect, and graph would be something like this. So we can simply say that this is the limit of proportionality. P stands for proportionality. This is the point which is, or let me draw it a bit curvy here, this way. Okay, and then this happens. Right. This is basically the point. This is the point. This one where elastic limit is approached. So you can simply say it is E or L. Okay, limit of elasticity or E कह सकते हो आप. This is U. This is the ultimate stress which can be withstand by a wire. Okay, U stands for ultimate stress. Yani this is basically the breaking point. This is what? The breaking point of the wire. So going back to that, we can take area of the graph, we can take gradient of the graph, everything. As if you now that if we take gradient of this graph, that will give you stress divided by strain, and what is equal to that one? Its gradient is Young's modulus, isn't it?
Yes.
Got it?
Yes.
Okay. Do you have any question?
Uh, no.
Not not at all. Okay. So that is equal to Young's modulus. So if I move on, I can say that the gradient of this
No.
graph will give you Young's modulus. Okay. Will you be able to recall it?
Yes.
And what about the area of this graph? Area of graph will give you something different. Area of the graph is strain, I mean 1 upon 2 strain times stress, or simply you can say stress times strains. So that is equals to 1 by 2. What is stress? Sorry, what is strain? E divided by L. And what is stress? That is F divided by A. So when you write this all in this way, 1 upon 2 F times E into 1 upon A times L. So is it understandable, or should I use any other format? Do you understand it? That what did I do?
Yes.
I just rearrange that, nothing else. I have multiplied A and L together, and I just combine F and E together. Okay? Is it clear to you? So 1 upon 2 F times E into 1 upon V volume, where area into length is equals to your volume. Clear? So what about this one? What was this? Yani this 1 upon 2F into E. It was your strain energy. Okay, boy? That is your strain energy. So finally, I can say that area of stress and strain graph is equals to energy per unit volume or strain energy per unit volume. Strain energy per unit volume, which is called your energy density, right? That is equals to energy density. Is it clear to you? So I can
Yes.
simply say that area of stress and strain, that is equals to energy per unit volume or energy density. Is it clear to you? So the area of your force and extension, that was equals to only energy, strain energy, but here you have energy density. Is it clear to you?
Yes.
Okay. Mostly this strain energy question is horrible when it is connected with your bungee jumper. Do you know about bungee jumper?
Yes.
Oh, well. So let's say this is a platform and a bungee jumper is just above the platform, standing above the platform, and there is a rope attached with that, and that rope or the string is just here. So at this point, what is the yani he is at rest over here. He is at rest. So its kinetic energy is equals to zero. Its potential energy, yani gravitational potential energy is maximum. And what about elastic potential energy? A strain energy. That is zero because string is not yet stressed. Are you getting my point? Hello?
Yes.
Strain energy is equal to zero. So let's say the boy is jumping down here, and at this point, the string is not yet stretched fully, and here is the bungee jumper. Do you have a laptop with you?
Yes.
Okay. So, are you using that?
Yeah, I'm entering from laptop.
You're taking notes from laptop?
Oh no.
Ah, no.
I mean, I'm using to enter the meeting.
Okay.
Whatever.
Okay. The rope is not yet stretched. Okay. So here, let's say this is point A, this is point B. At A, the kinetic energy is zero because that is at rest, because speed is zero. Gravitational, sorry, elastic potential energy is zero. Yani strain energy or EPE. I will shortly write it. EPE is zero. Why? Because your extension is zero, right? Rope is not yet extended. Then what about GPE? GPE is also equals to, that is not also equal to, that is maximum. But what about point B? This is your point B. At point B, KE is not equal to zero. EPE is still zero. Do you agree?
Yes.
GPE is not zero, but less than that of A. What? Are you getting my point?
Yes.
Okay. Now, at this point where bungee jumper has the highest, I mean, the lowest position of its motion, the rope is stretched. I mean, rope is stretching, actually not stretched. There are several diagrams I have to draw, man. Here, right here is that guy, and the rope is now stretched, not fully. Okay, the rope is yet stretched, but not fully. So at this point, this is your point C. So at C, what is happening? Yes, will you explain it to me? KE is not GP, sorry, EPE is not zero. GPE is not zero, right? Is it my point clear to you?
Yes.
None of the energy is maximum. All are basically varying. Kinetic is increasing, gravitational potential is decreasing. So I can say that KE at C is greater than KE at B, but GPE at C is less than GP at B. Got you? Did you get my point?
Yes.
This is the hardest question of strain energy and elastic potential energy part. Now, at the final stage, at this point, the rope is fully stretched. Bungee jumper is at the lowest position of its motion. Okay, this is the lowest point D. What is that point? That is your point D. This is your point D, lowest point. At this point, what is your expectation at D? Your KE is zero because it is stopped. Then it would be moved back, na? Are you getting the mechanism of bungee jumper?
I think, yeah.
Dekho, initially at point A, he's at the platform. At point B, he's in the path where rope is not yet started to be stretched. I mean, that is the path just after the jump. Point C is the point where he has fallen the height equal to the length of the rope, but not rope is not yet started stressed, right? I will write here that rope is still unstressed, but it is open to its highest length. Is it clear to you?
Yes.
This is string fully stressed. That's it. So when the string will be fully stretched, the bungee jumper would be at the lowest point and it is stopped momentarily. Its speed goes to zero. And from here, he will move upward. Is it? So kinetic goes to zero. GPE is not zero, but lowest, okay, smallest, and elastic potential energy. Elastic potential energy is not zero, but highest. Here, the largest energy which it has is elastic potential energy. Are you getting my point? So, if I ignore everything, and if I say that gravitational is also gone to zero, if I say, if assume, right, that GPE 0, KE 0, got it? Then what about EPE? Both of these energies are now lost, got it? And they all are converted to, so you can say loss in GPE plus loss in KE is equals to gain in EPE. Yeah, yeah. I told you this is the hardest topic. So my question is, from which point your kinetic started to decrease?
See.
Really?
Wait. Not
Yes.
yet.
Yes,
Yeah.
yes, yes. You're right. When the rope started to stretch, it would try to bring the body. Actually, this rope is break actually. So the as the object is falling down, it will it should gain the kinetic energy. But as it is losing the kinetic energy, it means that kinetic energy is used to stretch the rope. Are you getting my point?
Yes.
Okay. So this was what I had to discuss with you in elastic potential energy topic. Now go to another area, that is the types of materials. Just streaming चल रही है. Types of materials. So let me just go back, and we will be inshallah done with this chapter.